Tonight, we're going to talk about something on Mercury that sounds like it shouldn't be possible. On Mercury, a single day is longer than an entire year. Not by a little bit. A single day on Mercury, from one sunrise to the next, takes 2 full Mercury years to complete. That means if you were standing on Mercury's surface watching the sun cross the sky, the planet would orbit the sun twice before you ever saw a second sunrise. And it gets stranger. At certain points during that day, the sun would appear to rise, stop in the sky, move backward, stop again, and then resume moving forward. This isn't science fiction, this is real orbital mechanics, and the reason it happens is one of the most elegant and strange phenomena in the entire solar system. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you think you already understand. A day. You experience one every single time you wake up, go about your life, and go back to sleep. The sun rises in the east, climbs across the sky, sets in the west, and after a stretch of darkness, it rises again. That cycle, from one sunrise to the next, is what you call a day. It's the most basic unit of time in human life. Civilizations have been built around it. Clocks were invented to divide it. Your body's internal rhythms, your circadian rhythm, is locked to it. The day feels like the most natural, most obvious thing in the world. It's so obvious, in fact, that most people never stop to ask what's actually causing it. They know the Earth spins on its axis, and that spinning is what creates the cycle of day and night. The side facing the sun gets daylight. The side facing away gets darkness. As the Earth rotates, every point on the surface sweeps through both light and shadow. One full rotation equals one day. Simple. Except, it isn't quite that simple, because there are actually 2 different ways to measure how long it takes for a planet to rotate once, and the difference between them is at the heart of everything we're going to explore tonight. The first way is called a sidereal day. This is the time it takes for a planet to complete one full rotation relative to the distant stars. Imagine you're standing on Earth and you look straight up at night and pick a particular star directly overhead. A sidereal day is the amount of time it takes for the Earth to spin all the way around until that exact same star is directly overhead again. For Earth, a sidereal day is about 23 hours and 56 minutes, not 24 hours. 23 hours and 56 minutes. Most people don't know this. They assume a full rotation takes exactly 24 hours because that's how long a day is on the clock. But the clock isn't measuring a sidereal day. The clock is measuring something else. A solar day. A solar day is the time it takes for the sun to return to the same position in the sky. From noon to noon, or from sunrise to sunrise, however you want to think about it. For Earth, a solar day is almost exactly 24 hours. And that's the one that matters for everyday life, because we don't set our schedules by the stars. We set them by the sun. So why is the solar day slightly longer than the sidereal day? This is where it gets interesting and where the seeds of Mercury's strangeness are planted. The reason is that while Earth is spinning on its axis, it's also moving along its orbit around the sun. In the time it takes Earth to complete one full rotation relative to the stars, about 23 hours and 56 minutes, the Earth has also moved a little bit forward in its orbit. Because the Earth has shifted position, the sun is no longer in quite the same direction it was one sidereal day ago. The Earth has to rotate just a tiny bit more, about 1 degree more, to bring the Sun back to the same position in the sky. That extra bit of rotation takes about 4 minutes. And that's why the solar day is 4 minutes longer than the sidereal day. 23 hours and 56 minutes for the sidereal rotation, plus about 4 minutes of extra rotation to compensate for orbital motion, gives you a solar day of 24 hours. On Earth, this difference is so small that you'd never notice it in daily life. 4 minutes out of 24 hours is trivial. The sidereal day and the solar day are almost the same length. Your intuition about what a day is works perfectly fine. The sun comes up, the sun goes down, the sun comes up again. It takes 24 hours. Easy. Now let's talk about a year. A year is the time it takes for a planet to complete one full orbit around its star. For Earth, that's about 365 and a quarter days. The year is fundamentally different from the day because it's driven by a completely different motion. The day comes from rotation, the planet spinning on its axis. The year comes from revolution, the planet traveling around the sun. On Earth, the year is vastly longer than the day. 1 year contains about 365 days. This means Earth completes about 365 full rotations for every single orbit around the sun. The spin is fast. The orbit is slow. The day is short. The year is long. And this feels natural to us. It feels like the way things should work. Of course, a year is longer than a day. Of course, a planet spins many times during a single trip around its star. That just makes sense. But here's what most people never consider. There's no law of physics that says it has to work this way. There's no rule that requires a planet's day to be much shorter than its year. The rotation speed and the orbital speed of a planet are determined by completely different physical processes. How fast a planet rotates depends on how it formed, on the impacts it experienced early in its history, and on how tidal forces from its star and moons have altered its spin over billions of years. How fast a planet orbits depends on how far it is from its star, and how massive that star is. These are independent quantities. They don't have to relate to each other in any particular way. It just so happens that for Earth, the spin is fast and the orbit is slow. But that's not a universal law. It's just how things worked out for our planet. On other worlds, the relationship between day and year can be very different. And on one world in particular, it becomes so strange that it breaks your intuition entirely. But before we get to Mercury, let's look at how the other planets handle this relationship. Because seeing the range of possibilities helps us appreciate just how unusual Mercury really is. Mars is a good starting point because it's the most Earth-like in this regard. Mars has a rotation period of about 24 hours and 37 minutes, almost the same as Earth. If you were living on Mars, your days would feel familiar. The sun would rise on roughly the same schedule you're used to. But a Martian year is much longer than an Earth year, about 687 Earth days. So on Mars, 1 year contains about 668 Martian days. The ratio is different from Earth's, but the basic pattern is the same. Many days fit inside 1 year. The day is short, the year is long. Everything feels normal. Jupiter spins incredibly fast. Despite being the largest planet in the solar system, with a diameter of about 86,881 miles, Jupiter completes a full rotation in just under 10 hours. That's the shortest day of any planet in the solar system. If you could somehow stand on Jupiter's cloud tops, the sun would race across the sky, rising and setting in less than 5 hours. Meanwhile, Jupiter's year is almost 12 Earth years long, about 4,333 Earth days. So Jupiter packs more than 10,000 Jupiter days into a single Jupiter year. Again, lots of days per year. The day is short, the year is long, the pattern holds. Saturn rotates in about 10 hours and 40 minutes. Uranus rotates in about 17 hours. Neptune rotates in about 16 hours. All of them have years measured in decades. Earth decades, that is. And all of them contain thousands or tens of thousands of their own days within a single year. The pattern is so consistent across the outer solar system that you might start thinking, this is just how planets work. Many spins per orbit. Short days, long years. Then you get to Venus, and things start to go wrong. Venus rotates extraordinarily slowly. One full rotation relative to the stars takes about 243 Earth days. But Venus orbits the Sun in about 225 Earth days. This means Venus's sidereal day is actually longer than its year. The planet takes longer to spin once than it does to go all the way around the Sun. Already, this is a departure from everything we talked about. On every other planet we've discussed, the day is a small fraction of the year. On Venus, the sidereal day is longer than the year itself. And to make things even stranger, Venus rotates backward. Every other planet in the solar system, with the possible exception of Uranus, which is tilted on its side, rotates in the same direction it orbits. They spin counterclockwise when viewed from above the North Pole, and they orbit counterclockwise too. Venus spins clockwise. Its rotation is retrograde, meaning it goes in the opposite direction from its orbit. Nobody knows for certain why. The leading theory is that a massive collision early in Venus's history flipped it over or gradually reversed its spin through a combination of tidal effects and atmospheric dynamics. Because Venus rotates backward and very slowly, its solar day is actually shorter than its sidereal day. A solar day on Venus, from one sunrise to the next, lasts about 117 Earth days. That's shorter than its sidereal rotation period of 243 days. This might seem counterintuitive, but it happens because the backward rotation and the forward orbital motion partially cancel each other out when calculating the solar day. Still, a solar day of 117 Earth days is remarkable. It means that on Venus, the Sun takes nearly 4 Earth months to go from one sunrise to the next. You'd experience just under 2 Venus solar days for every Venus year. Venus is weird, but Mercury is weirder. And the reason Mercury is weirder isn't just because its numbers are strange. It's because the relationship between its rotation and its orbit is locked together in a very specific way that produces consequences unlike anything else in the solar system. Let me give you Mercury's basic numbers first, and then we'll dig into what they actually mean. Mercury orbits the Sun in about 88 Earth days. That's its year. 88 Earth days to make one complete trip around the Sun. That's the shortest year of any planet in the solar system, which makes sense because Mercury is the closest planet to the Sun. The closer you are to a star, the faster you orbit. Mercury zips around the Sun at an average speed of about 105,600 miles per hour. That's nearly 50 kilometers per second. For comparison, Earth orbits at about 67,000 miles per hour. Mercury is moving about 1.5 times faster. Now here's where it gets strange. Mercury's sidereal rotation period, the time it takes to spin once relative to the stars, is about 58.65 Earth days. If you just look at that number in isolation, It might seem like Mercury has a day that's shorter than its year. 58 days to spin once, 88 days to orbit once. So you'd expect about 1.5 Mercury days per Mercury year. You'd expect the day-year relationship to be unusual, but not fundamentally bizarre. But that conclusion would be wrong. Because the number that actually matters for someone standing on Mercury's surface isn't the sidereal day, it's the solar day. The time from one sunrise to the next. And Mercury's solar day is not 58 Earth days. Mercury's solar day is 176 Earth days. 176 Earth days from one sunrise to the next. That's 2 full Mercury years. The planet orbits the sun completely, comes all the way back to where it started, keeps going, completes an entire second orbit, and only then does the sun finally return to the same position in the sky. 1 solar day equals 2 Mercury years. Think about what that means for a moment. If you were standing on Mercury and you watched a sunrise, you would wait for Mercury to travel all the way around the sun. 88 Earth days would pass. Mercury would complete 1 full year, and the sun would not yet be back where it started in your sky. It wouldn't even be close. You would have to wait for Mercury to go around the sun a second time, another 88 Earth days, before you'd see the next sunrise. 2 complete orbits for 1 day. This is completely unlike anything on Earth. On Earth, you experience about 365 days per year. On Mercury, you experience half a day per year, less than 1 day per year. The planet orbits the sun faster than it cycles through a full day-night sequence. On Earth, the year is the long cycle and the day is the short cycle. On Mercury, it's reversed. The day is the long cycle and the year is the short cycle. And the ratio between them is exact. Not approximately 2 years per day. Exactly 2 years per day. This precision is not a coincidence. It's the result of a very specific physical mechanism that locks Mercury's rotation to its orbit in a precise mathematical ratio. And that mechanism is called spin-orbit resonance. Before we get into the details of that resonance, let me make sure you fully appreciate how bizarre Mercury's situation is by comparing it directly to Earth. On Earth, the solar day is 24 hours. The year is 8,760 hours. The ratio of year to day is about 365 to 1. On Mercury, the solar day is 176 Earth days, which is 4,224 hours. The year is 88 Earth days, which is 2,112 hours. The ratio of year to day is 1/2, not 365 to 1. 1/2. The year is half the length of the day. On Earth, hundreds of days fit inside a year. On Mercury, not even 1 full day fits inside a year. You need 2 years to get through a single day. If you tried to set up a calendar on Mercury based on days and years the way we do on Earth, it would make no sense. On Earth, we number the days within a year. Day 1, day 2, day 3, all the way up to day 365. On Mercury, you couldn't do that because a year doesn't contain a full day. Instead, you'd have to number the years within a day. Year 1 and year 2 of this particular day. It's completely backwards from everything you're used to. This also means that concepts we take for granted don't translate to Mercury at all. Think about the word morning. On Earth, morning is a specific time of day that lasts a few hours. You wake up, you have breakfast, and by midday you've moved on. On Mercury, morning would last weeks. The sun would rise so slowly, that you could watch it crawl above the horizon over the course of Earth days. The entire concept of a morning routine would be meaningless when morning itself spans more time than an entire Earth month. Noon on Mercury wouldn't be a moment, it would be an era. The sun at its highest point in the sky would hang there for weeks before slowly beginning its descent toward the opposite horizon. An afternoon on Mercury would outlast most vacations on Earth. And night on Mercury would be an 88-day stretch of darkness. An entire Mercury year of night before dawn finally arrives again. The temperature consequences are extreme. During the long Mercury day, the side facing the sun heats up to about 800 degrees Fahrenheit. That's hot enough to melt some metals. During the equally long Mercury night, the temperature plunges to about minus 290 degrees Fahrenheit. Mercury has essentially no atmosphere to trap heat or moderate these swings, so the temperature follows the sun with almost no buffer. When the sun is up, the surface bakes. When the sun is gone, the surface freezes. And these cycles of baking and freezing last for months at a time because the day itself lasts for months. Now, here's a question that might already be forming in your mind. Why is Mercury's solar day so much longer than its sidereal day? On Earth, the difference between the solar day and sidereal day is about 4 minutes. On Mercury, the sidereal day is about 58.5 Earth days, and the solar day is 176 Earth days. That's a difference of about 117.5 Earth days. The solar day is 3 times longer than the sidereal day. On Earth, the solar day is only about 0.3% longer than the sidereal day. On Mercury, the solar day is 200% longer than the sidereal day, 3 times as long. The reason for this enormous difference goes back to that fundamental distinction we talked about earlier. The solar day isn't just about how fast the planet spins. It's about how fast the planet spins relative to how fast it orbits. On Earth, the orbital motion is slow compared to the rotation. Earth moves about 1 degree per day along its orbit, while rotating 360 degrees. So the orbital correction needed is tiny. Just that 4 extra minutes of rotation each day to keep the sun on schedule. But on Mercury, the orbital motion is fast compared to the rotation. Mercury rotates about 6 degrees per day relative to the stars, but moves about 4 degrees per day along its orbit. The orbital speed and the rotational speed are much closer together. This means the correction needed to convert from sidereal to solar time is enormous. Mercury spins, but it's also hurtling around the sun so fast that the orbital motion almost keeps pace with the rotation. The sun doesn't fall behind as quickly as it does on Earth because Mercury's forward orbital motion keeps partially cancelling out the rotational motion. And because of the specific ratio between Mercury's rotation and orbit, the 3:2 ratio that we'll explore in detail shortly, the cancellation works out to produce a solar day that is exactly twice the orbital period. Exactly 176 Earth days. This is the first hint that Mercury's day isn't just weird by accident. It's weird because of a very precise mechanical relationship between how fast Mercury spins and how fast it orbits. These two motions are locked together like gears in a machine, and that machine is what produces all of Mercury's strange day-year behavior. What's amazing is that for decades, astronomers didn't even know this was happening. For over a century, the best scientific minds believe Mercury was tidally locked to the sun in a 1-to-1 ratio, just like the moon is tidally locked to Earth. They thought one side of Mercury permanently faced the sun, while the other side was locked in eternal darkness. That was the textbook answer. That's what was taught in universities. That's what appeared in scientific papers. And it was completely wrong. The truth didn't come out until 1965, when radar observations bounced microwave signals off Mercury's surface and measured how fast different parts of the surface were moving. The result showed that Mercury was rotating, not locked 1-to-1, but spinning with a period of about 59 Earth days. The planet wasn't showing one face to the sun at all. It was rotating, slowly, but definitely rotating. This discovery overturned decades of scientific consensus and revealed Mercury's true nature. Not a world frozen in a 1-to-1 lock with its star, but a world trapped in something far more unusual. A 3-to-2 spin-orbit resonance, a mechanical arrangement where the planet rotates exactly 3 times for every 2 trips around the sun. And it's this resonance that creates everything strange about Mercury's day. The bizarre solar day that lasts 2 Mercury years, the sun's retrograde motion in the sky, the impossible sunrises and sunsets. All of it traces back to this one locked ratio. 3 rotations for every 2 orbits. 3-to-2. It sounds simple, but the consequences are anything but simple. The consequences are some of the most mind-bending phenomena on any planet in our solar system. And to understand why this specific ratio exists, why 3-to-2 and not 1-to-1, why not some other number entirely, we need to understand what spin-orbit resonance actually is, how it works, and why Mercury's orbit made this particular resonance almost inevitable. To understand what's happening on Mercury, you need to understand a concept called spin-orbit resonance. And to understand spin-orbit resonance, the best place to start is with the most familiar example of it in the solar system, the moon. You've probably noticed that the moon always shows the same face to Earth. No matter when you look at it, no matter what phase it's in, you always see the same craters, the same dark patches, the same familiar pattern. The far side of the moon is permanently hidden from view. You can never see it from Earth's surface. This isn't a coincidence. It's the result of a physical mechanism called tidal locking, and it's a specific type of spin-orbit resonance. Specifically, it's a 1-to-1 spin-orbit resonance. Here's what that means. The moon takes about 27.3 Earth days to complete one orbit around Earth, and it takes exactly the same amount of time, 27.3 Earth days, to complete one full rotation on its axis. One rotation per orbit. 1-to-1. Because the moon rotates exactly once for every orbit it completes, the same hemisphere always faces Earth. The rotation and the orbit are perfectly synchronized. They're locked together like 2 gears meshing perfectly, turning at exactly the right rates to keep the same face pointed inward at all times. This didn't happen by accident. Early in the moon's history, it rotated faster. It spun at a different rate than it orbited, but Earth's gravity created tidal bulges in the moon's body, slight elongations in its shape, caused by the uneven pull of gravity across the moon's diameter. As the moon rotated, these bulges were carried out of alignment with the direction toward Earth. Earth's gravity pulled on those misaligned bulges, creating a torque that gradually slowed the moon's rotation. Over millions of years, this tidal torque drained rotational energy from the moon, slowing its spin until it matched its orbital period. Once the rotation rate equaled the orbital rate, the bulges stayed aligned with Earth, the torque dropped to 0, and the moon was locked, permanently synchronized. One rotation per orbit, 1 to 1. This is the simplest and most common type of spin-orbit resonance, and it's everywhere in the solar system. Pluto and its moon Charon are mutually tidally locked. They both show the same face to each other at all times. Most of the large moons of Jupiter and Saturn are tidally locked to their parent planets. Io, Europa, Ganymede, and many others all rotate once per orbit, always showing the same face to Jupiter. Tidal locking in a 1-to-1 ratio is the default outcome when a smaller body orbits close enough to a larger body for tidal forces to be significant over long time scales. And for over a century, astronomers believed Mercury was locked in this exact same way. They believe Mercury showed one face permanently to the Sun, while the other face was locked in eternal darkness. This seemed to make perfect sense. Mercury is the closest planet to the Sun. The Sun's tidal forces on Mercury are enormously powerful, far stronger than Earth's tidal forces on the Moon. If the Moon got tidally locked to Earth, then surely Mercury, which is so much closer to an object so much more massive, would be tidally locked to the Sun. One face in permanent blazing daylight. One face in permanent frozen darkness. A world divided sharply in half. The Italian astronomer Giove Arcni Schiaparelli, who studied Mercury extensively in the late 1800s, reported seeing the same surface features in the same positions whenever he observed the planet. He concluded that Mercury always showed the same face to the Sun, just as the Moon always shows the same face to Earth. Other astronomers confirmed his observations, or thought they did. The idea became scientific consensus. It appeared in textbooks, encyclopedias, and popular science books for decades. Maps were drawn showing a permanent day side and a permanent night side. Scientists speculated about what the boundary between light and dark would be like. A twilight zone where temperatures might be moderate enough for interesting chemistry. All of it was wrong. The problem was that Mercury is extremely difficult to observe from Earth. It's always close to the Sun in the sky, which means it's only visible near sunrise or sunset, when the atmosphere is thick and turbulent. Telescopic observations were blurry and unreliable. Astronomers were seeing what they expected to see. They expected Mercury to be tidally locked, so they interpreted ambiguous observations as confirming that expectation. It's a cautionary tale about how assumptions can corrupt even careful scientific observation. The truth was revealed in 1965. Astronomers Gordon Pettengill and Rolf Dice at the Arecibo Radio Telescope in Puerto Rico bounced powerful radar signals off Mercury's surface. By analyzing how the reflected signals were Doppler shifted, they could measure how fast different parts of Mercury's surface were moving toward or away from Earth. If Mercury were tidally locked 1-to-1 with the Sun, one side would always face the Sun, and the planet would rotate once every 88 Earth days, matching its orbital period. The Doppler measurements would show a specific pattern consistent with that rotation rate. But that's not what they found. The Doppler shifts indicated that Mercury was rotating with a period of about 59 Earth days, not 88. Mercury was spinning faster than a 1-to-1 lock would produce. This was shocking. It overturned a century of scientific consensus in a single observation. At first, the result was met with skepticism. Could there be an error in the measurements? Could the radar signals have been misinterpreted? But repeated observations confirmed the finding. Mercury was definitely rotating once every 58.65 Earth days, not once every 88 days. It was not tidally locked 1-to-1. And then someone noticed something remarkable about the numbers. Mercury's orbital period is about 88 Earth days. Its rotation period is about 58.65 Earth days. Divide 88 by 58.65, and you get almost exactly 1.5. The orbital period is exactly 1.5 times the rotation period. Or to put it another way, the ratio of Mercury's rotation period to its orbital period is almost exactly 2 to 3. This means that in the time Mercury takes to orbit the Sun twice, which is 176 Earth days, it rotates on its axis exactly 3 times. 3 rotations for every 2 orbits. A 3 to 2 spin-orbit resonance. Let me make sure this is absolutely clear because it's the key to everything. In a 1-to-1 spin-orbit resonance, like the Moon, the body rotates once per orbit. In Mercury's 3 to 2 resonance, the body rotates 1.5 times per orbit. For every single trip around the Sun, Mercury completes exactly 1.5 full rotations. After one orbit, Mercury has turned around 1.5 times, which means the side that was facing the Sun at the start is now facing away. After the second orbit, Mercury has completed 3 full rotations, and the same side is facing the Sun again. This is why Mercury's solar day is exactly 2 Mercury years. After one orbit, Mercury has spun 1.5 times, which means the Sun hasn't returned to its starting position in the sky. The planet has to go around again, completing a second orbit and finishing the 3rd rotation, before the Sun is back where it started. 2 orbits, 3 rotations, 1 solar day. But here's the deeper question. Why 3 to 2? If tidal forces from the Sun were strong enough to affect Mercury's rotation, and they clearly were, why didn't they lock Mercury into a 1-to-1 resonance like the Moon? Why did Mercury settle into this unusual ratio instead of the simpler, more common one? The answer lies in Mercury's orbit, and specifically in one property of that orbit that makes Mercury different from almost every other body that has been tidally locked in the solar system. Mercury's orbital eccentricity. Most orbits in the solar system are close to circular. Earth's orbit has an eccentricity of about 0.017. That means it deviates from a perfect circle by less than 2%. The Moon's orbit around Earth has an eccentricity of about 0.055, still fairly circular. The orbits of Jupiter's large moons are even more circular, with eccentricities close to 0. When orbits are nearly circular, tidal locking almost always produces a 1-to-1 resonance. The tidal forces are relatively constant throughout the orbit because the distance between the two bodies doesn't change much. The torque on any tidal bulge is steady and consistent, and it naturally drives the rotation towards synchronization with the orbital period. But Mercury's orbit is not circular. Mercury has the most eccentric orbit of any planet in the solar system. Its orbital eccentricity is about 0.206. That might not sound like much, but it means Mercury's distance from the Sun varies enormously over the course of a single orbit. At its closest point to the Sun, called perihelion, Mercury is about 29 million miles away. At its farthest point, called aphelion, it's about 43 million miles away. That's a difference of nearly 50%. Mercury is almost 1.5 times farther from the Sun at aphelion than at perihelion. This matters enormously because tidal forces depend very strongly on distance. Tidal force is proportional to the inverse cube of the distance. If you double the distance, the tidal force drops by a factor of 8. If you halve the distance, the tidal force increases by a factor of 8. Because Mercury's distance from the Sun varies so much during its orbit, The strength of the sun's tidal pull on Mercury also varies enormously. At perihelion, the tidal force is much stronger. At aphelion, it's much weaker. This variation is what makes the 3-to-2 resonance possible, and, in Mercury's case, more stable than a 1-to-1 resonance. To understand why, you need to think about what happens during the critical moment of closest approach. When Mercury is at perihelion, it's moving fastest in its orbit. This is a consequence of Kepler's second law, the law of equal areas. A planet sweeps out equal areas in equal times as it orbits, which means it moves faster when it's closer to the Sun and slower when it's farther away. At perihelion, Mercury is hurtling past the Sun at maximum speed. In a 3-to-2 resonance, every time Mercury passes through perihelion, it presents almost exactly the same orientation to the Sun. Not the same face, the way a 1-to-1 lock would, but the same elongated axis. Mercury, like most solid bodies, isn't perfectly spherical. It has a slight elongation, a tidal bulge, one axis that's slightly longer than the others. In the 3-to-2 resonance, this elongation is aligned with the Sun at each perihelion passage. Sometimes the long axis points toward the Sun with one end, and sometimes with the other end. But the alignment is always there at the moment when the tidal force is strongest. This alignment at perihelion is what stabilizes the resonance. If Mercury's rotation drifted slightly faster or slower than the 3-to-2 ratio, the elongation would be out of alignment at perihelion, and the strong tidal force at closest approach would pull it back. The resonance is self-correcting. It has a restoring force that keeps Mercury locked in the 3-to-2 ratio. For a 1-to-1 resonance to be stable, the alignment needs to hold throughout the entire orbit, not just at perihelion. In a circular orbit, this works fine because the distance and tidal force are constant. But in Mercury's highly eccentric orbit, the tidal force at perihelion is so much stronger than at aphelion that the perihelion alignment dominates. The 1-to-1 resonance, which requires continuous alignment, is actually less stable than the 3-to-2 resonance, which only requires alignment at the moments of strongest tidal interaction. Let me use an analogy. Imagine you're pushing a child on a swing. If you push at just the right moment, at the peak of the swing, when the child is moving most slowly, your push has the maximum effect. It doesn't matter what you do during the rest of the swing cycle. What matters is the timing of your push at the critical moment. The 3-to-2 resonance works similarly. The strong tidal kick at perihelion is the push. As long as Mercury's elongation is aligned at perihelion, the resonance is stable. What happens at other points in the orbit matters much less because the tidal force is so much weaker there. In a more circular orbit, the tidal force would be roughly the same everywhere. There wouldn't be a single dominant moment. In that case, a 1-to-1 lock would be more natural, because continuous alignment would be the most stable state. But Mercury's orbit isn't circular. It has a strong perihelion pulse, and that pulse favors the 3-to-2 resonance over the 1-to-1. There's another way to think about this. In a 1-to-1 resonance, the planet rotates once per orbit, and the same face always points toward the Sun. But for this to work in an eccentric orbit, the planet would need to change its rotation speed slightly during the orbit, spinning a little faster near perihelion and a little slower near aphelion, to keep the same face pointed sunward as its orbital speed changes. A rigid planet can't do this easily. Its rotation rate is essentially constant because angular momentum is conserved, and there's no mechanism to speed up and slow down the spin within a single orbit. In the 3-to-2 resonance, this problem doesn't arise in the same way. Mercury rotates at a constant rate, and the mathematical relationship between 1.5 rotations per orbit works out so that the elongation naturally aligns with the Sun at each perihelion, without requiring any variation in rotation speed. The 3:2 resonance is geometrically compatible with a constant spin rate in an eccentric orbit. The 1:1 resonance is not, or at least, it's much less stable. This is a genuinely elegant piece of celestial mechanics. The eccentricity of Mercury's orbit, which is a legacy of Mercury's formation and early orbital evolution, determine which resonance Mercury could settle into. A different eccentricity might have produced a different resonance, or a 1:1 lock, or no resonance at all. But Mercury's particular eccentricity made the 3:2 resonance the most stable attractor. Once Mercury's rotation slowed enough to approach this ratio, the resonance captured it and held it. Let's compare this directly with the Moon to make the contrast sharp. The Moon orbits Earth in a nearly circular path. Its eccentricity is only about 0.055. The tidal forces from Earth on the Moon are relatively constant throughout the Moon's orbit. There's no single dominant tidal pulse. The 1:1 resonance is the most stable option because continuous alignment is achievable in a nearly circular orbit. The Moon was captured into a 1:1 lock and has stayed there. Mercury orbits the Sun in a highly eccentric path. Its eccentricity is about 0.206, roughly 4 times the Moon's eccentricity. The tidal forces from the Sun on Mercury vary enormously during Mercury's orbit. There is a dominant tidal pulse at perihelion. The 3:2 resonance is more stable than the 1:1 resonance because it exploits the perihelion alignment without requiring constant alignment throughout the orbit. Mercury was captured into the 3:2 lock. Same physical mechanism, tidal interaction, same mathematical framework, spin-orbit coupling, but a different outcome because of a different orbital geometry. The orbit shapes the resonance, and the resonance shapes the day. Now, I want to address something that might be nagging at the back of your mind. Could other resonances be possible? Could a planet be locked in a 2:1 resonance, or a 5:3, or some other ratio? The answer is yes, in principle. Spin-orbit resonances can occur at any ratio where the numbers are small integers. 1:1, 3:2, 2:1, 5:2, and others. But not all resonances are equally stable, and which one a particular body settles into depends on the specifics of its orbit, its internal structure, and its history. The 1:1 resonance is the most common because it's the strongest and most easily captured. Most tidally influenced bodies end up in 1:1 locks. The 3:2 resonance is the next most stable in many scenarios, especially for bodies with significant orbital eccentricity. Higher order resonances like 2:1 or 5:2 are theoretically possible, but are generally much harder to capture and maintain. They require very specific conditions. In our solar system, Mercury is the only known planet or major moon in a 3:2 spin-orbit resonance. It's genuinely unique in this regard. There may be exoplanets around other stars in similar resonances, particularly those with eccentric orbits close to their host stars, but we haven't confirmed any yet. Mercury remains the only known example of this phenomenon among the major bodies in our cosmic neighborhood. The precision of Mercury's resonance is also worth emphasizing. Mercury doesn't rotate roughly 3 times for every 2 orbits. It rotates very precisely 3 times for every 2 orbits. The ratio is locked to within a very tight tolerance by the tidal restoring force. If some perturbation, a large asteroid impact for example, were to slightly speed up or slow down Mercury's rotation, the tidal interaction at perihelion would gradually push the rotation rate back toward the resonant value. The resonance is a stable equilibrium, like a ball sitting at the bottom of a bowl. Push it and it rolls back. This stability is what has kept Mercury in the 3:2 resonance for billions of years. The resonance was established early in Mercury's history, probably within the first billion years or so after the solar system formed, and it has persisted ever since. Mercury's rotation rate hasn't changed significantly in billions of years because the resonance holds it in place. Let me now connect the 3:2 resonance back to the numbers I gave you earlier, because seeing how the math works out is deeply satisfying. Mercury's orbital period is about 88 Earth days. If Mercury rotates exactly 1.5 times per orbit, then the rotation period should be 88 divided by 1.5, which equals 58.67 Earth days. The observed rotation period is 58.65 Earth days. The match is almost perfect. The tiny discrepancy is within measurement uncertainty. The 3:2 ratio is exact to within the precision of our measurements. Now, here's where the math produces the stunning result. The solar day, the time from one sunrise to the next, depends on both the rotation period and the orbital period. For a planet with prograde rotation, meaning it spins in the same direction it orbits, the solar day can be calculated from the sidereal day and the orbital period. When you do this calculation for Mercury using its 3:2 resonance, the solar day comes out to exactly 2 orbital periods, exactly 176 Earth days. Not approximately. Exactly. The 3:2 resonance mathematically guarantees that the solar day is precisely twice the year. This is not a coincidence and it's not an approximation. It's a mathematical consequence of the resonance. Any body in a perfect 3:2 spin-orbit resonance will have a solar day that is exactly twice its orbital period. The resonance determines the day, the orbit determines the year, and their ratio is fixed at exactly 2:1. This creates a relationship between day and year that is completely unique in the solar system. On Earth, the day and year are essentially independent quantities that happen to have a ratio of about 1 to 365. On Mercury, the day and year are locked together by the resonance, and their ratio is fixed at exactly 2:1. Change Mercury's orbital period and the solar day changes in lockstep, always maintaining that 2:1 relationship. This coupling between rotation and orbit is what makes Mercury's day feel broken. On most planets, the day is a rotation phenomenon and the year is an orbital phenomenon, and the two are largely independent of each other. On Mercury, the day is a hybrid. It's created by the interaction between rotation and orbital motion, and the two are permanently linked by the resonance. You can't understand Mercury's day without understanding its orbit, and you can't understand its orbit without understanding the resonance. Everything is connected. The 3:2 resonance also produces something else that's extraordinary, something that no 1:1 tidal lock would ever create. On Mercury, different longitudes experience different conditions at each perihelion passage. Remember, Mercury rotates 1.5 times per orbit. After one orbit, the planet has rotated 1.5 times, which means the face that was pointed toward the Sun at the previous perihelion is now pointed away. The opposite side faces the Sun. After 2 orbits, the planet has rotated 3 full times, and the original face is back toward the Sun. This means there are two special longitudes on Mercury, roughly opposite each other, that alternately face the Sun at perihelion. These are sometimes called the hot poles. At these longitudes, the Sun is directly overhead at the moment of closest approach to the Sun, when the solar radiation is most intense. These hot poles experience more extreme heating than any other location on Mercury's surface because they receive the most concentrated sunlight at the moment when Mercury is closest to the Sun. Other longitudes on Mercury experience perihelion when the Sun is lower in their sky, receiving less intense radiation. The variation across Mercury's surface isn't just about latitude, as it is on Earth. It's also about longitude, because the resonance creates a preferred orientation at the moment of maximum solar heating. Two specific spots on Mercury's equator get hotter than anywhere else, not because of anything about their geology, but purely because of how the 3:2 resonance positions them relative to the Sun at closest approach. This is one of the many ways that the 3:2 resonance shapes Mercury's world in ways that go far beyond simply defining how long a day is. The resonance determines the climate patterns, the temperature distribution, the thermal stress on the surface, even the long-term geological evolution of the planet. Mercury's entire physical character is sculpted by this one elegant mathematical relationship between spin and orbit. The 3:2 spin-orbit resonance is the engine behind everything strange about Mercury's day. It's the reason the solar day is exactly twice the year. It's the reason different phases of Mercury alternate in facing the Sun at perihelion. It's the reason Mercury has hot poles and warm poles. And as we'll see next, it's the reason Mercury has what might be the most bizarre sunrise in the entire solar system. A sunrise where the Sun comes up, reverses course, goes back down below the horizon, and then rises again. A double sunrise created entirely by the interplay between Mercury's steady rotation and its wildly varying orbital speed. An interplay made possible only because of the 3:2 resonance. The resonance doesn't just make Mercury's day longer than its year. It makes Mercury's day stranger than any day on any other planet. And the full strangeness only becomes clear when you try to stand on Mercury's surface and watch what the Sun actually does as it crosses the sky. That is the journey we take next. Because knowing the numbers is one thing, but seeing what those numbers look like from the ground, watching the Sun perform its impossible dance above Mercury's horizon, that is where the true wonder of this broken day reveals itself. Now let's do something that no textbook diagram can fully capture. Let's stand on Mercury's surface and actually watch what the Sun does. Because everything we've discussed so far, the 3:2 resonance, the 176 Earth day solar day, the ratio of exactly 2 years per day, all of that is abstract. It's numbers and ratios and orbital mechanics. But the real strangeness of Mercury's day only becomes vivid when you experience it from the ground. When you watch the Sun crawl across a Mercury sky and see it do something that would be physically impossible on any other planet in the solar system. Let's pick a location. We're going to stand on Mercury's equator at one of the longitudes where the Sun happens to be near the horizon, right as Mercury swings through perihelion, its closest approach to the Sun. These are the longitudes roughly 90 degrees away from the so-called hot poles, the spots where the Sun would be directly overhead at perihelion. The location we've chosen is the most dramatic place to witness what happens, though the basic phenomenon occurs at other longitudes too, with slightly different timing. We arrive at the start of a new solar day. The sun has just set below the western horizon. Mercury's surface is plunging into darkness. There's essentially no atmosphere to scatter light. No twilight glow, no gradual dimming. One moment the sun is a sliver on the horizon, and the next moment it's gone. The sky is black and full of stars. The temperature begins to drop. And it will keep dropping for a long time because night on Mercury isn't a few hours. It stretches across an entire Mercury year, roughly 88 Earth days of unbroken darkness. During this long night, Mercury is completing the first half of its solar day cycle. It's orbiting the sun, swinging around to the far side, and then coming back toward the starting area. And it's rotating, slowly, steadily, at its constant rate of 1.5 rotations per orbit. The stars wheel overhead in a pattern that would look unfamiliar to anyone used to Earth's sky. They move slowly, much more slowly than stars appear to move on Earth, because Mercury's rotation is so sluggish. On Earth, the stars appear to rotate once across the sky every 23 hours and 56 minutes. On Mercury, one full stellar rotation takes 58.5 Earth days. The stars barely seem to creep across the sky. Now, approximately 88 Earth days after sunset, after a full Mercury year of darkness, dawn finally approaches. The sun begins to peak above the eastern horizon, but it doesn't rise the way the sun rises on Earth. On Earth, the sun appears to climb briskly above the horizon, moving about 1 degree every 4 minutes, clearing the horizon entirely in roughly 2 to 3 minutes. On Mercury, the sun's motion is agonizingly slow. It takes Earth days, not minutes, for the sun to fully clear the horizon. You can watch the first sliver of light appear and then go take a nap lasting several Earth days, and wake up to find the sun still inching its way above the horizon. And there's something else you would notice as the sun clears the horizon. Something that would be deeply unsettling if you were used to the sun as seen from Earth. The sun looks enormous. From Earth, the sun appears to be about 1/2 degree across in the sky. That's roughly the width of your pinky finger held at arm's length. From Mercury, the sun is dramatically larger. How much larger depends on where Mercury is in its eccentric orbit, and this is where things become visually strange. At aphelion, when Mercury is at its farthest point from the sun, about 43 million miles away, the sun appears roughly twice as wide as it does from Earth. That's already noticeably bigger. But at perihelion, when Mercury swings to its closest approach of about 29 million miles, the sun swells to roughly 3.25 times the diameter it appears from Earth. The disk of the sun in Mercury's sky at perihelion covers more than 10 times the area it covers in Earth's sky. It's a blazing, oversized disk hanging in a black sky with no blue atmosphere to soften its glare. No haze, no clouds, just an enormous white sun against pure blackness. And here is what makes this truly eerie. Because Mercury's distance from the sun changes so dramatically during a single orbit, you would actually watch the sun change size during the course of a single Mercury day. As Mercury approaches perihelion, the sun visibly swells, growing larger over the course of weeks. As Mercury moves away from perihelion toward aphelion, the sun visibly shrinks. This isn't a subtle effect. The sun's apparent diameter changes by roughly a factor of 1.5 between aphelion and perihelion. If you could somehow photograph the sun at both extremes and lay the photos side by side, the perihelion sun would obviously, unmistakably, dwarf the aphelion sun. On Earth, The sun's apparent size barely changes throughout the year because Earth's orbit is nearly circular. The difference between perihelion and aphelion on Earth is only about 3%. Far too small to notice with the naked eye. On Mercury, the change is enormous and impossible to miss. The sun breathes. It swells and shrinks as Mercury swoops closer and then retreats farther from it during each orbit. And because one solar day spans 2 full orbits, you would witness this swelling and shrinking twice during a single day. The sun would grow as Mercury approached perihelion, shrink as Mercury moved toward aphelion, grow again during the second perihelion passage, and shrink again before finally setting. This pulsing sun would be the backdrop for everything else that happens in Mercury's sky. And at the double sunrise longitudes, the sun is at its largest and most intense precisely when it performs its backward dance near the horizon. The sun that rises, retreats, and rises again isn't just performing an impossible backward motion. It's doing it while swollen to its maximum apparent size, blazing with maximum intensity, looming on the horizon like something out of a fever dream. The combination of the backward motion and the oversized disk would be one of the most alien visual experiences anywhere in the solar system. But here's where it gets truly strange. And this is the part that makes Mercury's day unlike anything else in the entire solar system. At certain longitudes on Mercury, specifically near the intermediate longitudes where the sun is low in the sky during perihelion, the sun does not simply rise, cross the sky, and set. Instead, the sun rises above the eastern horizon, climbs a small distance into the sky, then stops. It hangs motionless for a period of time, then it reverses direction and sinks back down toward the eastern horizon. It sets back below the horizon it just rose from. The sky goes dark again. And then, sometime later, the sun rises a second time from the same eastern horizon. And this time, it continues its journey across the sky for real. This is the double sunrise, a phenomenon unique to Mercury. A sunrise that happens, unhappens, and then happens again. If you were standing at the right spot on Mercury's equator, you would watch the sun come up, watch it go back down, experience a brief second period of darkness, and then watch the sun come up again. All from the same horizon, all as part of the same solar day. On the opposite side of the planet, at the corresponding intermediate longitude, the same thing happens in reverse at sunset. The sun sets below the western horizon, the sky goes dark, then the sun peaks back above the western horizon briefly before setting again for good. A double sunset. This sounds impossible. On Earth, the sun never reverses direction. It rises in the east, crosses the sky, and sets in the west. Always. The motion is smooth, continuous, and unidirectional. The idea of the sun going backward feels like something out of a myth or a broken simulation. But on Mercury, it's real physics. And the reason it happens is the same 3-to-2 resonance we've been discussing, combined with Mercury's highly eccentric orbit. Let me explain the mechanism step by step, because once you understand it, it's one of the most beautiful examples of orbital mechanics, producing a visible, tangible consequence on a planet's surface. The apparent motion of the sun across a planet's sky is determined by 2 competing motions. The first is the planet's rotation on its axis. Rotation causes the sun to appear to move across the sky from east to west. The faster a planet rotates, the faster the sun appears to move. On Earth, rotation dominates. The sun moves across the sky primarily because Earth is spinning. The second motion is the planet's orbital movement around the sun. As a planet moves along its orbit, the direction to the Sun changes. This orbital motion also contributes to the Sun's apparent position in the sky. On Earth, this contribution is tiny because Earth moves only about 1 degree per day along its orbit while rotating 360 degrees per day. The rotational motion overwhelms the orbital motion by a factor of about 360 to 1. The orbital correction is just that 4-minute difference between the sidereal day and the solar day that we talked about earlier. You'd never notice it by watching the Sun, but on Mercury, the situation is fundamentally different. Mercury rotates slowly, completing one rotation in 58.5 Earth days. That's a rotational rate of about 6.1 degrees per Earth day. Mercury orbits quickly, completing one orbit in 88 Earth days. Its average orbital rate is about 4.1 degrees per Earth day. These two rates are much closer together than on Earth. The rotational motion is only about 1.5 times faster than the orbital motion, not 360 times faster. This means the orbital motion has a much larger effect on the Sun's apparent position in Mercury's sky. The Sun's movement across the sky is the difference between the rotational motion and the orbital motion. When the rotational motion is slightly faster than the orbital motion, the Sun appears to move slowly from east to west. When they're exactly equal, the Sun appears to stand still. And when the orbital motion temporarily exceeds the rotational motion, the Sun appears to move backward from west to east. That last scenario is exactly what happens near perihelion. Remember, Mercury's orbit is highly eccentric. At perihelion, Mercury is much closer to the Sun than at aphelion, and it moves much faster. Kepler's second law tells us that a planet sweeps out equal areas in equal times. When Mercury is closer to the Sun, it has to move faster along its orbit to sweep out the same area. At perihelion, Mercury's orbital angular velocity, the rate at which the direction to the Sun changes, temporarily exceeds its rotational angular velocity. Let me put numbers on this to make it concrete. Mercury's rotational angular velocity is constant at about 6.1 degrees per Earth day. This never changes. Mercury spins at the same rate regardless of where it is in its orbit. But Mercury's orbital angular velocity varies enormously because of the eccentric orbit. At aphelion, when Mercury is farthest from the Sun, its orbital angular velocity is only about 2.8 degrees per Earth day. At perihelion, when Mercury is closest, its orbital angular velocity surges to about 6.3 degrees per Earth day. That might not sound dramatic, but remember, Mercury's rotation rate is about 6.1 degrees per day. The orbital rate has just barely overtaken it. Compare these numbers. The rotation rate is 6.1 degrees per day, constant. The orbital rate varies from 2.8 degrees per day at aphelion to 6.3 degrees per day at perihelion. For most of Mercury's orbit, the rotation rate exceeds the orbital rate, and the Sun appears to move normally from east to west, though very slowly. But near perihelion, the orbital rate of 6.3 degrees per day just barely exceeds the rotation rate of 6.1 degrees per day. The margin is slim, only about 0.2 degrees per day. But that slim margin is enough. It's enough to make the Sun stop in the sky, reverse direction, and at the right longitudes, dip back below the horizon. During this interval, the Sun's apparent motion reverses. Instead of moving from east to west, the Sun appears to move from west to east. It goes backward. This reversal doesn't last the entire orbit. It only happens for a window of time centered on perihelion, when Mercury is close enough to the Sun for its orbital angular velocity to exceed its rotational angular velocity. As Mercury moves away from perihelion and its orbital speed drops, the orbital angular velocity falls back below the rotational angular velocity. The reversal ends, and the Sun resumes its normal east to west motion. Now, let's put this all together and walk through the complete sequence of events at one of these double sunrise longitudes. As Mercury approaches perihelion, the Sun has been slowly rising in the east and climbing into the sky. The motion is sluggish because the difference between rotation rate and orbital rate is small. Days pass between noticeable changes in the Sun's position. The Sun is low in the sky, not far above the horizon. Then Mercury reaches the zone near perihelion, where its orbital angular velocity begins to exceed its rotational angular velocity. The Sun appears to slow down in its eastward to westward climb. It pauses. For a brief time, it hangs motionless in the sky as the two rates are exactly equal. Then the Sun begins to slide backward, moving from west to east. It sinks back toward the eastern horizon. At these intermediate longitudes, this reversal happens when the Sun is still very close to the horizon. The Sun hasn't climbed far into the sky before the reversal begins, so the backward motion carries it all the way back down to the eastern horizon, and below it. The Sun sets in the east, the direction it rose from. The sky goes dark briefly. Mercury continues past perihelion. Its orbital speed begins to decrease as it moves away from the Sun. The orbital angular velocity drops back below the rotational angular velocity. The Sun's apparent motion switches back to the normal east to west direction. The Sun rises again from the eastern horizon, this time for good. It continues its slow climb across the sky, eventually reaching its highest point and then descending toward the western horizon over the course of many Earth weeks. That's the double sunrise. The Sun rises, retreats, and rises again, all caused by the temporary reversal of apparent solar motion near perihelion, all caused by Mercury's orbital speed briefly outrunning its rotational speed, all caused ultimately by the combination of the 3-to-2 resonance and the eccentric orbit. The experience at other longitudes is different but equally strange. At the hot pole longitudes themselves, where the Sun reaches its highest point in the sky right at perihelion, the reversal produces a very different effect. At these locations, the Sun doesn't dip below the horizon during the reversal, because it's too high in the sky for the backward motion to carry it all the way to the horizon. Instead, the Sun appears to slow down, stop, move backward for a while, stop again, and then resume forward motion. The Sun performs a loop in the sky, retracing part of its path before continuing onward. An observer at one of these longitudes would see the Sun approach the zenith, pause, slide backward along its track, pause again, and then continue forward past the zenith and toward the western sky. It would look as though the Sun had changed its mind, as though it started to descend and then decided to go back up again. The noon Sun would linger for an unnervingly long time, hanging near the zenith through the entire reversal period before finally moving on. At the two intermediate longitudes, where the Sun is near the horizon during perihelion, the reversal produces double sunrises and double sunsets. At the two hot pole longitudes, where the Sun is near the zenith during perihelion, the reversal produces a prolonged midday as the Sun lingers at its highest point. At all other longitudes, the reversal happens somewhere in between, with the sun executing its backward loop at some intermediate elevation in the sky. Let me give you an analogy to help make this more intuitive. Imagine you're sitting on a merry-go-round that's spinning slowly. You're watching a friend who's walking around the outside of the merry-go-round in the same direction it's spinning. From your perspective on the merry-go-round, your friend appears to be moving slowly past you, because both you and your friend are moving in the same direction. You're rotating, they're walking, and the apparent motion you see is the difference between the two. Now imagine your friend suddenly starts jogging. They speed up so that they're moving faster than the merry-go-round is spinning. From your perspective, your friend appears to reverse direction. They were moving one way across your field of view, and now they're moving the other way because they're overtaking the merry-go-round's rotation. They haven't actually changed direction. They're still walking the same way, but from your rotating frame of reference, they appear to have reversed course. This is essentially what happens on Mercury. Mercury's rotation is the merry-go-round. The sun's apparent motion across the sky is like watching the friend. Near perihelion, Mercury's orbital motion speeds up, like the friend breaking into a jog. The orbital motion overtakes the rotational motion, and from Mercury's surface, the sun appears to reverse direction. The sun hasn't actually changed direction. Mercury hasn't reversed its rotation. The sun is still the same sun in the same place, but the combination of steady rotation and variable orbital speed creates the illusion, the very real observational reality of the sun going backward. Now let's talk about what all this does to the experience of time and environment on Mercury's surface. Because the double sunrise isn't just an astronomical curiosity, it has real physical consequences. Consider the temperature. Mercury has essentially no atmosphere. There's a thin exosphere, a wispy collection of atoms blasted off the surface by solar wind and micrometeorite impacts. But it provides no insulation, no greenhouse effect, no moderation of temperatures. The surface temperature at any given point is determined almost entirely by whether the sun is up and how high it is in the sky. At the hot pole longitudes, where perihelion coincides with the sun near the zenith, the surface temperature reaches its absolute maximum. The sun is at its closest, its radiation most intense, and it's shining straight down. Surface temperatures at these locations reach about 800 degrees Fahrenheit. That's hot enough to melt some alloys. Hot enough that if you laid a sheet of tin on the surface, it would liquefy. And at the hot poles, the reversal makes things even worse. The backward loop means the sun lingers near the zenith for an extended period, spending extra time near its highest point instead of smoothly crossing from one side to the other. This produces a prolonged period of maximum heating. The surface bakes under an almost overhead sun for longer than it would on a planet without this resonance effect. At the double sunrise longitudes, the heating cycle behaves differently. Here the sun rises, begins to warm the surface, then reverses and sets again. The surface starts to cool during the brief second night. Then the sun rises again and heating resumes. This creates a stutter in the temperature curve, a brief dip in the middle of what would otherwise be a smooth warming trend. The surface heats up, cools slightly, then heats up again. It's a small effect in terms of the overall temperature cycle, but it's a measurable one, and it's caused entirely by orbital mechanics, not by weather or atmosphere or anything else. Compare all of this to Earth. On Earth, the sun's motion across the sky is smooth and predictable. It rises, crosses the sky at a steady rate, and sets. The heating cycle is correspondingly smooth. Morning warming, midday peak, afternoon cooling, nighttime cold. The cycle repeats every 24 hours. There are no reversals, no double sunrises, no lingering noon sun. The angular speed of the sun across Earth's sky is almost perfectly constant throughout the day because Earth's orbital contribution is negligible compared to its rotational speed. Mars is similar to Earth in this regard. Its day is about 24 hours and 37 minutes, its year is about 687 Earth days, and the sun crosses the Martian sky smoothly and predictably. The orbital contribution to the sun's apparent motion is small, just as it is on Earth. Venus, despite its extremely slow rotation and retrograde spin, doesn't exhibit the double sunrise phenomenon either. Venus's orbit is nearly circular, with an eccentricity of only about 0.007. Because there's almost no variation in Venus's orbital speed, there's no moment where the orbital angular velocity surges past the rotational angular velocity. The sun on Venus moves very slowly across the sky, and it rises in the west because of the retrograde rotation. But its motion is smooth and continuous. No reversals, no double sunrises. The double sunrise requires two specific conditions working together. First, the rotation and orbital rates must be close enough that the orbital rate can sometimes exceed the rotational rate. Mercury's 3:2 resonance ensures this. Second, the orbit must be eccentric enough that the orbital speed at perihelion is significantly faster than the average orbital speed. Mercury's eccentricity of about 0.206 ensures this. Without both conditions, the phenomenon doesn't occur, and Mercury is the only planet in our solar system where both conditions are met. Let me walk you through one more perspective on this to really drive the point home. Imagine you could hover above Mercury's north pole and watch the planet from above, like looking down at a spinning top on a table while the table itself orbits a lamp in the center of the room. You'd see Mercury rotating counterclockwise, slowly. You'd also see it orbiting the sun counterclockwise, at a rate that varies depending on its distance from the sun. For most of the orbit, the rotation is winning. Mercury turns faster than the line between Mercury and the sun sweeps around. The sun-facing longitude shifts slowly westward, meaning the sun appears to move from east to west, as seen from the surface. Normal sunrise, normal sunset. But as Mercury rounds perihelion, its orbital motion surges. The line from Mercury to the sun sweeps around faster than Mercury is rotating. The sun-facing longitude shifts eastward. The sun, from the surface, appears to reverse direction. Watching from above, you'd see the subsolar point, the spot on Mercury's surface where the sun is directly overhead, crawling slowly westward for most of the orbit, then briefly reversing and sprinting eastward during the perihelion passage, then resuming its westward crawl. This eastward sprint during perihelion is what causes the double sunrise at some longitudes and the lingering noon at others. The total backward motion of the sun during the perihelion reversal is relatively small, a few degrees of arc, but near the horizon, where the sun is close to the edge of visibility, even a few degrees of backward motion is enough to carry the sun below the horizon and back up again. That's why the double sunrise only occurs at certain longitudes. The reversal is the same everywhere on Mercury, but only at the longitudes where the sun happens to be near the horizon during perihelion does the backward motion push it below the horizon. This entire phenomenon exists because of the precise mathematical coupling between Mercury's spin and orbit. If Mercury were spinning even slightly faster or slower, If it were not in the 3-to-2 resonance, the relationship between rotational and orbital angular velocity would be different. The reversal might not happen at all, or it might happen at a different time, producing a different pattern of sunrises and sunsets. The 3-to-2 resonance doesn't just determine how long Mercury's day is. It choreographs the sun's entire performance across Mercury's sky. Every pause, every reversal, every double sunrise is a direct consequence of that locked ratio between spin and orbit. The resonance is like a musical time signature that dictates the rhythm of Mercury's day. And that rhythm is unlike anything heard on any other world. Standing on Mercury, watching the sun perform its impossible backward dance near the horizon, you would be witnessing one of the most extraordinary consequences of orbital mechanics in the entire solar system. A consequence that was unknown to science until just decades ago. A consequence that overturned a century of incorrect assumptions about what Mercury's day looked like. A consequence that exists only because of the unique combination of Mercury's 3-to-2 resonance and its eccentric orbit. Two features that together create a day so strange that it challenges everything you thought you knew about how days and nights are supposed to work. The sun on Mercury doesn't just rise and set. It rises, retreats, and rises again. It lingers, reverses, and lingers again. It performs a slow, complex ballet dictated by the interplay of rotation and orbit, a ballet choreographed by tidal forces that locked Mercury into its resonance billions of years ago. And that raises the natural question: how did this happen? How did Mercury end up in this specific resonance? What was Mercury like before the resonance captured it? And what forces conspired over billions of years to slow its spin and lock it into this extraordinary state? That story begins in the earliest days of the solar system, when Mercury was a young world spinning much faster than it does today, and the sun's gravity was just beginning its patient, relentless work of reshaping Mercury's rotation into the broken, beautiful thing it is now. 4.5 billion years ago, Mercury did not have the day it has now. When Mercury first formed from the swirling disk of gas and dust that surrounded the young sun, it was a very different world. It was hot, partially molten, bombarded by debris left over from planetary formation, and most importantly for our story, it was spinning much faster than it does today. We don't know exactly how fast young Mercury rotated, but we can make educated estimates based on how planets form. Planets accumulate their spin from the material that builds them. As countless smaller bodies, rocks, dust, and planetesimals collide and merge to form a planet, the angular momentum of all those collisions adds up. The result is a planet that rotates. How fast it rotates depends on the specifics of those collisions, but for rocky planets in the inner solar system, initial rotation periods of somewhere between 5 and 20 hours are considered reasonable by most planetary formation models. So early Mercury probably had a day that lasted somewhere in that range. Maybe 10 hours, maybe 15. The exact number doesn't matter as much as the basic fact. Mercury's original day was short, measured in hours, not in months. The sun rose and set rapidly. Day and night cycled quickly. Mercury was, in this one regard, not so different from Earth or Mars or any other rocky planet in its youth. But Mercury had a problem that the other rocky planets did not share. It was close to the sun. Extremely close. Mercury orbits at an average distance of about 36 million miles from the sun. For comparison, Earth orbits at about 93 million miles. Mercury is less than 40% as far from the sun as Earth is, And that proximity meant that the sun's gravitational influence on Mercury was enormous. Not just in terms of keeping Mercury in orbit, which is true for all the planets, but in terms of the tidal forces the sun exerted on Mercury's body. Tidal forces arise because gravity isn't uniform across an extended object. The side of Mercury facing the sun is closer to the sun than the side facing away, so it feels a slightly stronger gravitational pull. This difference in gravitational pull across Mercury's diameter creates a stretching effect. The planet gets very slightly elongated along the line connecting it to the sun. The near side bulges toward the sun, and the far side bulges away from the sun. Now, if Mercury were perfectly fluid, like a ball of water, these tidal bulges would always point directly toward and away from the sun. As Mercury rotated, the bulges would stay aligned with the sun, and the fluid would simply flow to maintain that alignment. But Mercury isn't perfectly fluid. It's a rocky body with some rigidity. It takes time for the material of the planet to deform in response to the changing tidal force. This means the bulges don't point exactly toward the sun. They get carried slightly ahead of the Sun-Mercury line by the planet's rotation. This misalignment is the key to everything. Because the bulge is carried slightly ahead of the direct Sun-Mercury line, the sun's gravity pulls on it at an angle. That angled pull creates a torque, a twisting force that acts against the direction of Mercury's rotation. It's like dragging a brake on a spinning wheel. The torque doesn't stop Mercury instantly. It's incredibly subtle, but it acts continuously, every single rotation, for billions of years. Over geological time, this tidal torque gradually, relentlessly, drains angular momentum from Mercury's spin. The process is called tidal despinning, and it's the same mechanism that locked the moon into its one-to-one resonance with Earth. Earth's tidal forces created bulges on the moon. The moon's rotation carried those bulges ahead of the Earth-Moon line. Earth's gravity pulled on the misaligned bulges, creating a torque that slowed the moon's rotation. Over hundreds of millions of years, the moon's spin decreased until it matched its orbital period, at which point the bulges aligned permanently with Earth, the torque vanished, and the moon was locked. The same fundamental process happened on Mercury, but with the sun as the tidal source instead of Earth. The sun created bulges on Mercury. Mercury's rotation carried those bulges ahead of the Sun-Mercury line. The sun's gravity pulled on the misaligned bulges, creating a torque that slowed Mercury's rotation. Over hundreds of millions or billions of years, Mercury's spin decreased from its original fast rotation, maybe 10 or 15 hours per day, down through progressively longer rotation periods, 20 hours, 50 hours, hundreds of hours. The despinning was slow but inexorable. The sun never stopped pulling, and Mercury never stopped slowing down. But here's where Mercury's story diverges from the moon's story. The moon, orbiting Earth in a nearly circular orbit, was inevitably captured into a one-to-one resonance. As the moon's rotation rate decreased and approached its orbital rate, the one-to-one resonance captured it cleanly. The circular orbit meant there was no competing resonance strong enough to intercept the moon before it reached the one-to-one lock. Mercury's situation was different because of its orbital eccentricity. As Mercury's rotation slowed, it didn't approach the one-to-one resonance directly. Instead, it had to pass through other possible resonances first. And the first major resonance it encountered, the 3-to-2 resonance, was strong enough to capture it. Think of it like a ball rolling down a series of steps. Each step represents a possible spin-orbit resonance. The ball starts at the top, rolling fast, representing Mercury's initially rapid rotation. As it rolls down, it passes potential stopping points: the 3-2 resonance, the 2-1 resonance, and eventually the 1-1 resonance at the bottom. In a circular orbit, the intermediate steps are shallow. The ball rolls right past them and lands at the bottom, the 1-1 lock. But in an eccentric orbit, the 3-2 step is deeper. It's a real trap, a genuine energy minimum that can capture the ball and hold it. Mercury's eccentricity of about 0.206 made the 3-2 resonance deep enough and stable enough to capture the planet's slowing rotation before it could reach the 1-1 state. Once Mercury's rotation rate decreased to the point where it was completing approximately 1.5 rotations per orbit, the resonance grabbed hold. The tidal interaction at perihelion, the strong gravitational kick that occurs every time Mercury swings past its closest approach to the Sun, locked Mercury's elongation into alignment at perihelion. The restoring force of the resonance took hold, and Mercury's spin stabilized at the 3-2 ratio. This capture wasn't necessarily inevitable. Theoretical studies have shown that the probability of capture into the 3-2 resonance depends sensitively on Mercury's orbital eccentricity at the time of capture, and on the internal properties of the planet, particularly how dissipative its interior is. Dissipation refers to how efficiently the planet converts tidal energy into heat. A more dissipative interior, one that absorbs tidal energy more readily, increases the probability of capture at the 3-2 resonance. A less dissipative interior makes it more likely the planet would have passed through the 3-2 resonance and continued slowing toward the 1-1 lock. Physicists Peter Goldreich and Stanton Peele published a groundbreaking analysis of this problem in 1966, just 1 year after the radar discovery of Mercury's true rotation. They calculated that if Mercury had its current orbital eccentricity at the time of capture, the probability of being trapped in the 3-2 resonance was only about 7% for typical assumptions about Mercury's internal dissipation. That's surprisingly low. It suggested that Mercury was somewhat lucky to end up in the 3-2 resonance rather than the 1-1. However, more recent analyses have revised these numbers significantly. Researchers Alexandre Correa and Jacques Lascar published work in the early 2000s, showing that if Mercury's eccentricity was higher in the past, which is plausible given the chaotic evolution of the inner solar system's orbits, the capture probability increases dramatically. At an eccentricity of about 0.325, the 3-2 resonance becomes the most probable outcome, not a lucky accident. And there's good reason to think Mercury's eccentricity may have been higher billions of years ago. Gravitational interactions with the other inner planets, particularly Venus, can pump up Mercury's eccentricity over time and then allow it to decrease. If Mercury passed through a period of higher eccentricity early in its history, capture into the 3-2 resonance could have been the expected outcome rather than a fluke. Mercury's internal structure also plays a crucial role in this story. Mercury has the largest iron core proportionally of any planet in the solar system. The core makes up about 85% of Mercury's radius and about 60% of its total mass. For comparison, Earth's core makes up about 55% of its radius and about 32% of its mass. Mercury is essentially a giant iron ball, with a thin, rocky shell around it. This enormous core matters for the spin-orbit resonance in two ways. First, the core affects the planet's moment of inertia, which determines how the planet responds to tidal torques. A body with more mass concentrated toward its center, which is what a large, dense core does, has a lower moment of inertia relative to its mass. This affects how quickly the planet's rotation responds to tidal forces, and how easily it can be captured into a resonance. Second, and perhaps more importantly, Mercury's core creates a permanent asymmetry in the planet's mass distribution. Mercury isn't a perfect sphere. Even ignoring the tidal bulge, Mercury has a slight permanent elongation, a triaxial shape where one equatorial axis is slightly longer than the other. This permanent elongation is called the permanent quadrupole moment, and it's likely related to the freezing and solidification of Mercury's interior over geological time. As parts of the core solidified, they locked in slight asymmetries that make the planet permanently non-spherical. This permanent elongation is what the sun's tidal force grabs onto at perihelion. It's the handle by which the resonance holds Mercury in place. Without a sufficient permanent elongation, the 3-to-2 resonance would be weaker and potentially unable to hold Mercury's rotation. The fact that Mercury has a large core that froze in a slight asymmetry is part of what makes the 3-to-2 resonance stable. There's also the question of whether Mercury's core is fully solid or partially liquid. Data from the Messenger spacecraft, which orbited Mercury from 2011 to 2015, revealed that Mercury's core is at least partially liquid. The evidence came from measurements of Mercury's libration, a tiny wobble in the planet's rotation caused by the varying tidal force during its eccentric orbit. The amplitude of this libration was larger than it would be if Mercury were completely solid. A partially liquid core allows the outer rocky shell to wobble more than it would if the entire planet were rigid. A partially liquid core has implications for the resonance. The liquid portion of the core doesn't rotate rigidly with the rest of the planet. It can slosh and flow, partially decoupling from the mantle and crust. This changes the effective moment of inertia that participates in the spin-orbit coupling and affects the dissipation of tidal energy within the planet. Models that include a partially liquid core generally find higher probabilities of capture into the 3-to-2 resonance compared to models that assume a fully solid planet. So Mercury's resonance isn't just a product of its orbit, it's a product of its entire physical makeup. The large iron core, the permanent shape asymmetry, the partial liquidity of the core, the orbital eccentricity, and the relentless tidal torque from the sun all conspire together to produce the 3-to-2 lock. Change any one of these factors significantly, and Mercury might have ended up in a different rotational state. A higher eccentricity might have produced a higher order resonance. A circular orbit might have produced a 1-to-1 lock. A different core structure might have changed the capture probability entirely. The discovery that Mercury was in a 3-to-2 resonance rather than a 1-to-1 lock came as a shock in 1965, because no one had seriously considered the possibility. The assumption of 1-to-1 locking had been so deeply embedded in the scientific literature that the alternative wasn't even on the table. When Gordon Pettengill and Rolf Dice at Arecibo measured Mercury's true rotation period, the result contradicted almost a century of confident scientific claims. But the discovery did more than just correct an error about Mercury. It opened an entirely new field of study. Before 1965, Spin-orbit resonances other than the one-to-one lock were theoretical curiosities. Nobody knew of a real example. Mercury provided the first confirmed case, and it forced planetary scientists to take the full range of possible resonances seriously. It showed that planets don't just get tidally locked in the simplest possible way. They can get trapped in exotic intermediate states, depending on the details of their orbits and interiors. The Italian celestial mechanic Giuseppe Colombo was one of the first scientists to fully explain the 3-to-2 resonance after the Arecibo discovery. He worked out the mathematical details of how the resonance operates, how the perihelion alignment stabilizes it, and why Mercury's eccentricity made this resonance the likely outcome. His work laid the foundation for all subsequent studies of Mercury's rotational dynamics. But Colombo did something else that connected his theoretical brilliance to the practical exploration of Mercury. He realized that a spacecraft traveling to Mercury could use Venus as a gravitational slingshot, swinging past Venus to bend its trajectory and lose enough energy to drop into the inner solar system toward Mercury. This gravity assist technique, which Colombo proposed and championed, made the first mission to Mercury possible. That mission was Mariner 10. Launched in November of 1973, Mariner 10 became the first, and for decades, the only spacecraft to visit Mercury. Following the trajectory Colombo had designed, it swung past Venus in February of 1974, using the planet's gravity to redirect itself toward Mercury. Mariner 10 made 3 flybys of Mercury, in March and September of 1974, and again in March of 1975, before its fuel ran out and contact was lost. The images and data Mariner 10 sent back were revelatory. For the first time, humanity saw Mercury's surface up close. It was heavily cratered, resembling the moon in many ways, but with important differences. The most dramatic feature Mariner 10 discovered was the Calorus Basin, one of the largest impact craters in the solar system, roughly 950 miles across. The impact that created it was so violent that seismic waves traveled through the planet and converged on the opposite side, creating a chaotic jumble of fractured terrain called the Weird Terrain. Mercury's surface told a story of violent bombardment early in its history, the same period when the planet's rotation was being gradually slowed by solar tides. But Mariner 10 had a limitation built into the very resonance it was there to study. Because of the geometry of its orbit and Mercury's 3-to-2 resonance, every time Mariner 10 flew past Mercury, the planet presented the same face toward the Sun and roughly the same face toward the spacecraft. Mariner 10 ended up photographing the same hemisphere all 3 times, leaving nearly half the planet completely unseen. It was a cosmic irony. The very resonance that makes Mercury's day so strange also conspired to hide half the planet from our first robotic visitor. It would be more than 30 years before another spacecraft visited Mercury. The Messenger mission, which arrived at Mercury in 2011, provided a wealth of new data that refined our understanding of the resonance. Messenger measured Mercury's gravity field, its shape, its libration amplitude, and its surface composition with unprecedented precision. Unlike Mariner 10, Messenger entered orbit around Mercury rather than just flying past, which meant it could study the entire planet. It mapped the hemisphere Mariner 10 had never seen and confirmed the global nature of Mercury's cratered, geologically complex surface. These measurements allowed scientists to constrain Mercury's internal structure, and improve models of how the resonance operates and how stable it is. The BEPE Colombo mission, a joint project between the European Space Agency and the Japan Aerospace Exploration Agency, arrived at Mercury in 2025 and is expected to provide even more detailed measurements. This mission carries instruments specifically designed to study Mercury's interior through gravitational and rotational measurements. It will improve our understanding of Mercury's core structure and the mechanics of the 3-to-2 resonance. Now let's step back and consider the broader significance of Mercury's broken day. Because Mercury isn't just interesting as a one-off curiosity, it teaches us fundamental lessons about how tidal interactions shape worlds throughout the solar system and beyond. Earth's own day is being affected by tidal forces right now. The moon's gravity creates tidal bulges on Earth, and just as the sun's gravity slowed Mercury's rotation, the moon's gravity is slowing Earth's rotation. Earth's day is getting longer, not by much. The rate of lengthening is about 1.4 milliseconds per century. That's almost nothing on a human timescale. You would never notice it in your lifetime. But over geological time, it adds up enormously. 600 million years ago, during the Cambrian period when complex animal life was first appearing, an Earth day was only about 21 hours long. A billion years ago, it was about 18 hours. Early in Earth's history, when the moon was much closer, a day might have been as short as 6 to 8 hours. The moon has been gradually slowing Earth's rotation for over 4 billion years, and it will continue to do so for billions of years to come. Will Earth ever become tidally locked to the moon? In theory, yes. Given enough time, tidal forces would slow Earth's rotation until it matched the moon's orbital period, and the same face of Earth would always point toward the moon. But this would take tens of billions of years, far longer than the sun's remaining lifespan. The sun will expand into a red giant and likely consume or char the Earth long before tidal locking is complete. Mercury's fate was different because the sun's tidal forces were so much stronger due to proximity, and Mercury had billions of years for the process to play out. The lesson extends beyond our solar system. As astronomers discover more and more exoplanets, planets orbiting other stars, the question of tidal interactions becomes increasingly important. Many known exoplanets orbit very close to their stars, much closer than Mercury orbits the Sun. These planets experience tidal forces far more intense than anything in our solar system. Many of them are almost certainly tidally influenced in some way, with their rotation slowed or locked by their star's gravity. For exoplanets in nearly circular orbits, one-to-one tidal locking is the expected outcome. Many of the rocky exoplanets in the habitable zones of red dwarf stars, the most common type of star in the galaxy, are thought to be tidally locked. Stars like Proxima Centauri and the TRAPPIST-1 system host planets close enough that tidal locking is almost inevitable. These planets likely have a permanent day side and a permanent night side, with enormous temperature contrasts and unique climate dynamics. But what about exoplanets in eccentric orbits? Mercury teaches us that eccentric orbits can lead to spin-orbit resonances other than one-to-one. An exoplanet with significant eccentricity could be trapped in a 3-to-2 resonance, just like Mercury, or possibly in a 2-to-1 resonance, or a 5-to-2, or some other ratio. Each resonance would produce a different day-night cycle, a different pattern of heating and cooling, a different climate. The habitability of such a world would depend critically on which resonance it's trapped in. A planet in a 3-to-2 resonance would have a solar day twice as long as its year, just like Mercury. If that planet were in the habitable zone of its star, the long day could have profound implications for its climate. One side would bake for an extended period, while the other froze. An atmosphere could help redistribute heat, but the day-night temperature contrast would still be far more extreme than on a rapidly rotating planet like Earth. Weather patterns would be fundamentally different. Wind systems would be driven by the enormous temperature gradient between the sunlit and dark hemispheres. Mercury's example shows us that we can't simply assume all close-in exoplanets are tidally locked one-to-one. We need to consider the eccentricity of their orbits, the structure of their interiors, and the history of their tidal evolution to predict what kind of day they actually have. Mercury is the template, the proof of concept that shows other outcomes are not just theoretically possible, but physically realized. There's something philosophically striking about Mercury's situation. Mercury's day is broken in the sense that it violates our intuitive expectations about how days and years should relate to each other. On Earth, the day-year system is simple and intuitive. Many short days fill a long year. Sunrise follows sunrise in a rapid, predictable rhythm. The sun moves smoothly across the sky. Time feels orderly. On Mercury, nothing about the day-year system is intuitive. The day is longer than the year. 2 years fit inside one day. The sun rises, goes backward, and rises again. The concepts of morning, noon, and evening lose their familiar meaning when each one lasts for weeks. A calendar based on Mercury's day and year would look nothing like any calendar humans have ever devised. It would need to track years within days rather than days within years. And yet, Mercury's day isn't really broken. It's perfectly consistent with the laws of physics. Every aspect of it. The long solar day, the 3-to-2 resonance, the double sunrise, the retrograde solar motion, all of it follows inevitably from Newton's laws of motion, Kepler's laws of planetary motion, and the physics of tidal interactions. Nothing about Mercury violates any physical law. The only thing it violates is our expectations, our assumptions, our intuition built from living on a world where the day-year relationship is simple. Mercury reminds us that the universe doesn't care about our intuition. The laws of physics produce whatever outcomes the initial conditions and the forces dictate. Sometimes those outcomes align with our expectations. Sometimes they produce worlds where the sun rises twice, where a day contains 2 years, where the most basic rhythm of existence, the cycle of light and darkness, behaves in ways that no one on Earth would ever predict, without doing the mathematics. And the mathematics, once you work through it, is beautiful. The 3-to-2 resonance is an elegant solution to a complex physical problem. It's the natural outcome of tidal forces acting on a body with the right combination of orbital eccentricity and internal structure. It produces a solar day that is exactly twice the orbital period. Not approximately, but exactly, locked in by the same tidal forces that created the resonance in the first place. There's a precision and a beauty to it that you don't always find in planetary science, where things are usually messy and approximate. Mercury's day is the product of 4.5 billion years of gravitational sculpting. The sun's gravity reached across 36 million miles of space, gripped Mercury's slight elongation, and over eons dragged its rotation down from a fast spin to the slow, locked rhythm it has today. The eccentricity of Mercury's orbit, itself a product of the complex gravitational dance of the inner solar system, determined which resonance would capture that slowing spin. Mercury's massive iron core, its permanent shape asymmetry, and its partially liquid interior determined how the tidal energy was absorbed and how firmly the resonance would hold. Every detail of Mercury's day traces back to fundamental physics: gravity, angular momentum, orbital mechanics, tidal dissipation, the internal structure of a rocky planet. All of it comes together to produce a world where the sun performs an impossible dance across the sky. A world where sunrise happens twice. A world where day and year are locked in an elegant, unbreakable ratio. A world where the most ordinary thing you can imagine, the simple rising and setting of the sun, becomes one of the strangest phenomena in the solar system. The next time someone tells you they understand what a day is, that it's just the time from one sunrise to the next, remember Mercury. Remember that on one small rocky world, the closest planet to our star, the simple concept of a day becomes something so complex, so counterintuitive, and so beautiful that it took humanity centuries to even realize we had it wrong. Mercury's day isn't broken. It is just following rules we never thought to imagine. Rules written by gravity, shaped by time, and locked in place by a resonance that has held steady for billions of years, quietly making Mercury's sunrise the strangest in the solar system.